Now we'll talk a little more about independence. We know the definition for two events being independent is that P of A intersection B is just the product of the two probabilities. But what if I want to say that three events are independent? Is it enough to say that the probability of A and B and C is equal to the product of A times the product of B times the product of C? This might be our first guess. So is this enough? Well, it turns out that it isn't, but it's part of what's required. An example of when this holds, but events aren't independent, is let's say A is equal to, I roll two dice, so roll two dice again. Roll two dice. Let's say A is first shows 1, 2, or 3. B is first shows 3, 4, or 5. And C is the sum is 9. Okay, well, I think you could agree that these aren't independent, because if I knew that the first die showed a 1, 2, or a 3, you would probably say it's less likely that the sum is a 9 than if I didn't tell you that. Since it could only be a 9 if I actually got a 3. And you can work out the probabilities if you're still not sure. However, let's look at the intersection and let's look at the product. Well, the intersection, the first die shows a 1, 2, or 3. The first shows a 3, 4, or 5. So A intersection B is equal to anything where the first die is a 3. So it's 3, 1, 3, 2, all the way up to 3, 6. But only one of these, namely this guy, the sum is a 9. So A intersection B intersection C is equal to 3, 6. And the probability of this, so P of A intersection B intersection C, is equal to 1 over 36. Now let's work out the product. Well, all of the outcomes are equally likely, so probability of A is a half. The probability of B is a half. And what's the probability that the sum is 9? Well, we could get 3, 6. We could get 4, 5. We could get 5, 4. Or we could get 6, 3. So this is C. And the probability of C, well, that's just 4 over 36, or it's going to be 1 divided by 9. But what do we have here? P of A times P of B times P of C is equal to a half times a half times a ninth, and that's equal to 1 over 36 also. But we just said these events are not independent, at least by our intuition. So this clearly isn't enough. So what else do you think we would need? Well, what else is there? We need the pairs to be independent. So we say that three events are independent if P of A and B is P of A times P of B, P of A and C equals P of A times P of C, and P of B and C equals P of B times P of C, and this is all in addition to this condition up here. So we need all four of these conditions. These three are called pairwise independence. So this is pairwise independence. And then I guess triple independence. I don't remember the term for this. So you need all of these. Now, we'll also show that these conditions alone are not enough to guarantee that the three events are independent. For this example, let's go back to flipping two coins. Oops, didn't mean to bring that up. For this example, let's go back to flipping 2 coins. So we have, let's say A be the first coin is heads. So that's heads, tails, heads, heads. Let B be the event that the second coin flips up heads. So we have tails, heads, and we have heads, heads. Now let C be the event where the number of heads that I see is even. So heads, heads, 2 heads, and tails, tails, 0 heads. So are they pairwise independent? Well, the probability of A is a half, the probability of B is a half, and then we have the product is a quarter, and the intersection only contains heads, heads. Okay, this is good. Now, the probability of A and C, that also only contains heads, heads, so this is a quarter, and the probability of each of them is a half, so that's good. Now, same here, probability of B and C, they only share heads, heads, and so that's a quarter. This is a quarter, and then I multiply 2 halves together. That's good. So what about the probability of A and B and C? Well, this is equal to a quarter because the only event they all share is a quarter. But if I multiply them all together, P of A, P of B, P of C, well, that is going to equal an eighth, and that's definitely not a quarter. So what went wrong here? We can think about it in terms of our intuition, and our intuition says, well, if I tell you that the first coin is heads, and I tell you that the second coin is heads, then I know something about C. So if I know both of these, then I know something about C. I know that it's not tails, tails. But if I only know one, if I only know that I'm in A, if I only know that one of these events happened, that, or rather, yeah, if I only know, sorry, I think that's the wrong way to think about it in this case. Let's draw a picture that helps with intuition a little. So let's say that this is my sample space again. And if I have, say, tails, tails over here, heads, tails over here, tails, heads over here, and heads, heads over here, then my sets are, well, this is A, this is B, and this is C. So what happens is, if I know whether A happened and I know whether B happened, then I know exactly whether C happened. So A and B, knowing them together, gives me perfect information about whether or not C happened. So if I tell you A happened, you know it's heads, tails, or heads, heads. And if I tell you B happened, you know that it's either tails, heads, or heads, heads. But if I tell you that they both happened, then you know it's heads, heads. And if I tell you that they both didn't happen, then you know it's not heads, heads, and you know that it's not tails, tails. So if I know two of the events, I know exactly whether or not the third happened. And that is why they're not this three-way independent.